Hey y'all, it's your main math teacher, Mr. Boyden, back at it again today, and today we're going to talk about how to sketch graphs and determine symmetries, and a little bit about circles too. So I have a question on the screen for you to start with today to figure out, are either of these two given points solutions to the equation that's given below? So perhaps pause the video and try that now. Here's how it goes. We said earlier that a solution is simply the number or set of numbers that when input makes an equation work or makes it true. So all I would do to test these, if I wanted to test the point 1, 2, I would put in a 2 for y and see, does that equal 3 times 1 squared minus the square root of 1? Well, let's see. 1 squared times 3 is 3. So that says 3 minus 1 equals 2. So is this a solution? Yes, it is. What about 5, 13? Let's see. Is it true that 13 equals 3 times 5 squared minus root 5? All right. Well, 5 squared is 25. Times 3 is 75. And so already it's pretty clear that this is a big fat no. No, it doesn't work. So one was a solution, one was not. But today we're talking about graphs. So what does this mean for us in terms of graphs? Well, what it tells us, since this one worked out, since it was a solution, that tells us that 1, 2 is on the sketch of the curve of this equation, while 5, 13 is not on the curve produced by this equation. Let's look at what we're doing today. Okay, we're going to graph functions by plotting points, including using intercepts and symmetries, and we're going to look at equations of circles. So let's not waste any time. Let's get right into it. One method to generate graphs is to use a table of values, and this works really well when you don't know what a graph looks like. The downside is that it takes a long time. So what we're going to want as we move forward in this unit is we're going to want to look for patterns that are shortcuts, because this is definitely not a shortcut. For today, I want to use -2, -1, 0, 1, and 2 as my x values, and I think you'll see why it produces a nice little graph over here in a second. Okay, all we're going to do is we're going to plug these x values into the equation that was given. So what does that look like? Minus -2 squared plus 5. Notice my use of parentheses here. Okay, so what happens? We have a negative getting squared, so that's +4, but there's a minus in front of it. So we end up with -4 plus 5, and that's 1. Let's see, -2, 1. Let's go to the next one. Very similar steps. -1, square that up, add 5. That's -1 plus 5, so that's 4. So -1, 4. Keep going. Hey, this is an easy one. -0 squared plus 5. We could do mental math on that one. That's just 5, and that's nice. Here we can plug in a 1, so -1 squared plus 5. Again, notice the parentheses. We're going to honor PEMDAS. You have to square before you introduce the negative. So 1 squared is 1. Bring the negative, so you get -1 plus 5. All right, and there's 4, so 1, 4. Hey, it looks like it has y-axis symmetry. Let's see. So I'm now going to bring a 2, so I have -2 squared plus 5. That gives me -4 plus 5, so I have 1. So, y'all, you may recognize this from your algebra class. This is a parabola. Okay, so I'm going to sketch through it as best I can on my little touchpad here, and we know that keeps going. So it takes a little bit of time. There are definitely shortcuts that exist that make this quicker, but this will work every time, and so that's one thing that's really nice about this method. What about method 2? In this method, we're going to graph by using the intercepts. Okay, a little bit more algebraic, a little bit less guess and check. Okay, so when does this one work? It works really well when you know the basic shape of the graph, and maybe you'll need to get a few extra points like we did in method 1, but oftentimes this will be enough. Okay, how does it work? Well, let's talk about what it means to have an intercept. An intercept simply is any time when the graph that you're sketching hits the y-axis or the x-axis. So specifically, when we look at the y-intercept, it means we're hitting the y-axis. So what can you tell me about the coordinates of a point that's on the y-axis? Well, we should know that the x value is 0 and the y value is something. So what we know is that x equals 0. What about the x-intercept? An x-intercept is any time we hit the x-axis. So what can you tell me about the coordinates of any point along the x-axis? Well, you should be able to tell me that it could be left or right, but it's not up and down. So yeah, it's some x value, but we know the y value is 0. Okay, so if you ever get these mixed up, just pause and think about it. Like literally, what do I know about the coordinates of any point on the y-axis? Yeah, I know that x would be 0, and then you can keep it straight. Notice, if it's y-intercept, x equals 0, x-intercept, y equals 0. So let's do an example down here now and see if we can figure this one out. So let's first do our y-intercept. Okay, we just said that's when x equals 0, so our work will look like y equals 0 squared minus 4. So what do I get? I get y equals negative 4. All right, let's go over and sketch that. So my y value is negative 1, 2, 3, 4. Okay. And let's go to the next one. Now we're going to do the x-intercept. And for this one, we said that the y value is going to be 0. So I'm going to plug in a 0 for y, and I'm going to leave x alone. All right, and then we get to do some algebra steps. I'm going to add 4 to both sides, and then I'm going to take a square root, and we're going to remember that anytime we introduce the square root, if the context allows it, and that's different from the last video, right? The context does allow it this time. We're going to get positive and negative 2. So I get positive 2, and I get negative 2. So I said this technique works really well when we know the shape of the graph. I've chosen another quadratic, so it's going to be a parabola, but this time it doesn't seem like it opens down. It seems like maybe it opens up, and it absolutely does. Oh, I missed. Okay, so make sure you don't miss. I have a little bit of trouble drawing on this touchpad, but make sure you don't miss on those. Okay, so that's our second method. Let's get just a little bit more practice with the algebra of these. I don't think one example is quite enough. So this would be a really good time to pause the video, make your notes look really nice, and try these 3. We're going to find the intercepts, both x and y intercepts of each of these. Here's how it goes. We said for the x-intercept, that's where y equals 0. And you can do the y-intercept if you want first. I just picked x randomly. Okay, so 0 equals x squared plus 2x. Okay, and what I notice here is these both have an x in common, so I can factor that out. Okay, and then what do I get? I want to know what values of x would make this true, so I get x equals 0, and I get x equals negative 2. So those are my x-intercepts. Let's now do the y-intercept. Okay, for that, I know that I'm plugging in a 0, so y will equal 0 squared plus 2 times 0. All right, y'all, I really like finding y-intercepts. They're typically pretty easy because most stuff cancels out. In this case, everything cancels out, and it's 0. Okay, let's do the next one. Okay, for the next one, we're going to do our x-intercept. I'm kind of making a little table here. Okay, so I get 0 equals the negative absolute value of 2x plus 5. Oops, absolute value over here, I'm sorry. Okay, and so then the question is, well, what will make this true? Well, let's divide out the negative. Okay, the negative goes away. And then we need this stuff in here to be 0. So functionally, because this number is 0, the absolute value doesn't actually do anything because there is no positive or negative 0. So logically, this is equivalent to just 2x plus 5 equals 0. And then we can subtract 5 and divide by 2, and we see that x equals negative 5 halves. What about the y-intercept? Okay, that would be y equals negative absolute value of 2 times 0 plus 5, absolute value. And then 2 times 0 is 0, plus 5 is 5, so negative absolute value of 5. And this can frustrate people sometimes when they're learning, because they say, wait, but absolute value says it's always going to be a positive answer. Totally. Okay, y'all, this chunk is positive, but there's a negative in front of it, so it is actually going to be a negative answer. And I've heard that many times. People say, you can't have a negative answer when there's an absolute value. You definitely can. All it's saying is the stuff inside of the absolute value gets turned positive, then that negative is going to come down with it. Okay, and here's how the last one goes. Okay, down here, we're going to get 0 equals root x plus 2. Okay, we can square both sides to get rid of the root. Hey, it does nothing. So we get 0 equals x plus 2, and then we'll subtract the 2 to get x equals negative 2. And then down here, we get y equals the square root of 0 plus 2, which is just going to be root 2. Okay, so not too bad. We also need to talk about the symmetries that graphs can have. Okay, and so we have three different kinds of symmetries shown here. There are others, but there's three that we're going to focus on. The first one is called y-axis symmetry. Okay, and here's what I'd like you to see. If you pick a point, like let's say right here, at 1, 1, it has what I call a partner point, and that's not really what it's called, but I'm calling it a partner point that's on the other side of the y-axis. Okay, so it's sort of got its mate over there, and the coordinates on this one are -1, 1. Okay, and that works for any point. That's up here as well. Okay, if we have 2, 4, it will have a partner point on the other side of the y-axis, and it's the same coordinates except the x value is opposite. So -2, 4. So I'm going to make a little note here that when you have y-axis symmetry, the rule goes that there will exist a point that has the opposite x value and the same y value for any point. And it doesn't matter which point you pick, it'll have its opposite point. Now, I picked the ones that have integers as their values, so I was only able to find 2, but for any point that would be true. Okay, what about the next one? Where is the line of symmetry in this graph? This one is the x-axis that's cutting this in half. Okay, and it still has that same partner point relationship. So for example, if I pick this point right here, 1, 3, it has a point that is reflected on the other side, a partner point that is 1, -3. Okay, same out here. This little guy has a partner point down there. They have a point that is reflected across the axis. So it holds up with the relationship that for every point there will be a partner point of the form where the x value is the same and the y value is opposite. And then this last one, this is called origin symmetry, or symmetry about the origin. Okay, and so what that means is that for any point I pick, it has a partner point on the opposite side of the origin. Okay, and the way that works is if I could draw a perfectly straight line down to there, it'll always go through the origin. Every point will have a partner. So here's one here. It has a partner point somewhere out over here. That if I draw a line, a segment through the origin, the midpoint, or if I connect the 2 points, their midpoint will be the origin. So that'll happen for every point. So what does that mean? If we're up here in positive land, quadrant 1, and you have its partner point down here, negative, what that tells us is that for every point on this graph, there exists another point of the form such that the x value is opposite and the y value is opposite. So origin symmetry is incorporating both aspects, the aspect of y-axis, where you have an opposite x value, and of x-axis symmetry, where you have an opposite y value. It just has both. Okay, that's all. Let's do a little practice visually identifying these symmetries. So take a look at these 4 graphs and try to identify which symmetry each of them has. The first one has origin symmetry. Every point has a partner point that is across the origin. Okay, this one's got a point over here, this one's got a point over there. It has that relationship. What about here? I'll make a little origin symmetry. What about this one? Does it have a partner point for every point? It seems to. It's very curvy, but yeah, it absolutely is. This is also origin symmetry. What about down here? Each point has a point across the y-axis. This is y-axis symmetry. What about this one? What symmetries does it have? Let's see. Does it have a point across the y-axis? Nope, that's not on the graph. Does it have a point across the... No, it's not on the graph. Does it have a partner point across the origin? No. This one is a trick question. This one doesn't have any symmetries, so I'm going to put none, or has none of the 3 symmetries we talked about anyway. So, quick concept question before we continue. We've talked about 3 types of symmetry. How many can a single graph have? We know that it can have one kind of symmetry. Can it have 2? Can it have all 3? Is that possible? And then what we'll talk about in the next lesson is, could it be a function? So let's see. Could I draw a graph that has x-axis symmetry and y-axis symmetry, but not origin symmetry? Let's see. I'm thinking something like this. So that one has y-axis symmetry. I could reflect it across down here. Okay, and I didn't mean to leave a gap there. So now every point has a partner across the x-axis. Every point has a partner across the y-axis. But unwittingly, I've accidentally caused it to have a point across the origin as well, automatically. Interesting. I can't just do x and y without also having origin. It'll also automatically have origin. What if I tried to do one that had x-axis and origin symmetry? So maybe x-axis symmetry would look like this. And then if I had origin symmetry here, I'd have to put something like that over there. And to be origin symmetry with this, I'd have to have something like this over there. And hey, I have 3 kinds of symmetry again. It automatically happened. So that actually answers this question. How many can we have? We can have 1. We can have all 3 kinds of symmetry. We cannot have 2. There's no way to draw a graph that has exactly 2 of these types of symmetry. Kind of strange. So, what if it's not practical to draw out a sketch of the graph we have? Maybe for time reasons or something like that. You don't have enough time. Okay, if all we have is the equation, how can we tell the symmetries of the function? Like, for example, this one. Okay, now remember, we said if we have x-axis symmetry, then we will always have the point x comma negative y that's also on that line. If we have y-axis symmetry, then for every point, the point that is the opposite of x and the same as y will be on that same function. And for the last one, or the same graph, I should say, not necessarily a function. And for origin symmetry, we said that for any point, negative x, or the opposite of x, and the opposite of the y value will exist for any point. So algebraically, we can test the function that we have here. What we're going to do is we're going to plug these in, substitution style, and we're going to try to see if we can work them back to the original form. If we can, we'll know the graph has that symmetry. And if it's not possible, we'll know the graph does not. So let's start with x-axis symmetry. What that would look like is instead of y, we'll write negative y. And that's all. We'll try to simplify it. So negative y equals 3x squared minus 7. Now what I have to do is I have to try to work this algebraically so that it matches the original again, and that will prove that this is a solution to the original equation. So I got to get rid of that negative. It doesn't match right now. So I'm going to multiply both sides by negative 1, and you got to do it on both sides. So what do I get when I do that? I get y equals negative 3x squared plus 7. All right, I fixed the problem that the y was negative. Now they match again. However, I've created 2 new problems. What I can already see is that every time I fix a problem, it's going to generate a new problem. Something is going to have the wrong sign on it. So what does that tell me? It tells me this isn't going to be possible. So does it have x-axis symmetry? No, it doesn't. Okay, let's try y-axis symmetry. Okay, for this one, now I'm going to plug in a negative x instead of x. So it'll say y equals 3 times negative x squared minus 7. Let's try to simplify. So what we have here is we're squaring a negative x. Do you remember what happens when you square a negative? It goes positive. So just by pure simplification, this goes right back to its original form. So I hope you can see this matches perfectly what we were given. So does it have y-axis symmetry? Yes, it does. It has y-axis symmetry. So what symmetries does it have? It has y-axis symmetry. Now, before we try origin symmetry, ask yourself the question, is it possible that it has origin symmetry? Based on what we said a minute ago, we said that any graph can have one of the 3 types of symmetry, or it can have all 3. It cannot have 2. We already have a no, we have a yes. So if it had origin symmetry, then it would have 2 types, but not the 3rd. We know that's impossible. So rather than showing the work, I'm just going to say no, it can't. We know it can't have exactly 2 types of symmetry. We know it can have exactly 1 though. So this is done. Let's do another example. This would be a great one for you to try on your own and then hit play. All right, let's do x-axis first. So when we're doing x-axis symmetry, we are plugging in the point. Which one's negative? Is it the x or the y? The y. Okay, let's plug that in. So I get x times negative y squared plus 2 equals 0. When you square a negative, it goes positive. So I get xy squared plus 2 equals 0. Hey, that matches. So yes, it has x-axis symmetry. Let's test for y-axis symmetry. For y-axis symmetry, we plug in the point negative x comma y. Let's see what happens when we do that. I get negative xy squared plus 2 equals 0. All right, that's close. It doesn't quite match. It's pretty close, though. Let's see if we can make that positive. Let's maybe multiply by negative 1 on both sides. And so what I get then is I get xy squared. Hey, that's looking good. That matches. But when I distribute the negative, I get a negative 2 equals 0. So I've fixed one problem, but that fix has generated a new one. How would I fix this 2 being negative? I would have to multiply by negative 1 again, which would create the original problem again. So this is a big, fat no. All right, what about the last one? Origin symmetry. Now remember, you can have one of the 3 types, or you can have all 3 of the types. You could have none. We have 1, you can't have 2. So it couldn't be a yes, so origin symmetry is a no on this one. We would have plugged in a negative x, negative y, but because one of these passed and one failed, we don't have to. If both passed, yeah, we'd plug it in. If neither of them passed, yeah, we'd plug in the negative x, negative y, but if only one of them passes, there's no point, it won't work. We know that every time. So now we're going to talk a little bit about circles, and then we'll get out of here. All right, first of all, you got to think, what is a circle? Okay, great, it's a round thing. Totally get that. A circle is quite a lot more than a round thing, because ellipses or ovals, there's all sorts of round things. You could even argue parabolas are round. But what specifically defines a circle? From any one point, a circle is the collection of points that are an equal distance from that point. There are infinitely many of these points, and that's why they form a continuous loop. Okay, so one of the things about that feature, because you have a radius that is that common distance to every point, is you could express a circle as a series of triangles. Okay, now usually we don't, but think about this, right? You could have, this is one triangle that goes to a point on the circle, and here's a red triangle that goes to a point on the circle, and here's a purple triangle that goes to a point on the circle. And you could have infinitely many of those. I could draw another one here if I wanted, and then that goes straight down. So now I've got 4 triangles that all have a point at the origin and a point on the circle. So here's the question. What do every one of these right triangles have in common? There's something that is the same for each of them. Each of them have the exact same hypotenuse. So look at how these are organized. They each have a length that goes just left and right, a length that goes just up and down. Hey, that left and right length, let's call that x. That up and right, let's call that y. In fact, I'll draw one out here just so we can see. Okay. That left and right, we'll call that x. That up and down, we'll call that y. And if they all have the same length here, well, typically we'd call that r. So notice what I can do here, and this ties into the previous lesson. Right now, I have a right triangle, and I know the side lengths, so I can get x squared plus y squared equals r squared. That actually leads right into the equation for graphing a circle. Okay, because the actual equation goes like this. Okay, x minus h squared plus y minus k quantity squared equals r squared. A minute ago I had x squared plus y squared equals r squared. Here's the difference. X squared plus y squared equals r squared. That is a circle that is centered at the origin. But it would be nice to be able to put circles at different places, not always at the origin. So what this does, introducing h and k is the center point of the circle, and r is the radius. So it's kind of cool. Circles are actually an application of the Pythagorean theorem. Who knew that would come up so much? Okay, so let's look at this example down here. What do we know about this circle? Do we know its center? Yeah, well, we're told that h and k, we're told that h and k are the center point. So what do we know? We know this one has a center at 6, negative 3, and a radius of, all right, a lot of people say 9. It's actually 3. Let's talk about why. Okay, first things first. A lot of people want to say the center is negative 6, 3, because we can see a negative 6 sitting right here. But notice, these already have minuses in there. So when it says x minus h, it's saying that h is the center, not negative h is the center. Okay, so it's just literally whatever number's sitting there. What's going on over here is you have to imagine this formula said y minus, and then if we had a negative 3 there, minus a negative would have led to a plus. That's why it's a negative 3 that we pull out to there. And then what about this 9 down here? You'll say, wait, I thought the radius was 9. But notice, this says r squared. That says 9. So what do we know? We know r squared equals 9. If you square root both sides, you get 3. Why don't you also get negative 3? Okay. Circles cannot have a negative radius. Circle has a positive radius. So yes, we introduced a root. However, you have to make sure the context allows for a negative number. Okay, what about this circle? Do we know about this one? H and K are not named. Hey, we kind of already talked about that, didn't we? That means the center is at the origin. What's the radius on this one? Okay, the radius is actually 1. Well, what gives? Okay, this was a 9, and we had to modify that to get a 3 for the radius. This one's a 1, and the radius is 1. All it is that if r squared is 1, which is what this says, when you take a square root, the square root of 1 is still 1. Okay, so the radius is 1 on that one. So let's practice actually answering a couple questions now that we've done some interpretation. Okay, we're going to write the equation of a circle, which has a center at 2, negative 1, and a radius of 5. Okay, here we go. So the equation goes, the quantity x minus the x value of the center, so 2 squared, plus, let's see, y minus, now normally it's a minus, but we always put the opposite of what we see. It would be like y minus negative 1. So I'm going to put a plus 1, and that's also squared, equals 5 squared. Now I'm going to actually square it. 5 squared is 25. So I hope you see how we can look at this information and just directly write out the answer. We don't have to do a bunch of simplification steps because we know how to square that in our head. Okay, and we have one more and we'll be done. We're going to try to write out the equation of a circle whose center is at the origin and which has 2, 2 as a solution point. So do you notice what piece of information seems like it's missing right now? Normally, we would need to know the radius. It's not given. We can actually figure it out. Okay, so what do I know about a circle that's centered at the origin? That would be x minus 0, quantity squared, plus y minus 0, that's the origin, 0, 0, squared equals, I don't know the radius, so r squared. I'm going to simplify that to get x squared plus y squared equals r squared, and they were kind enough to give me a solution point, meaning when I plug these in, it does not violate the equation. So let's plug them in. So that would be 2 squared plus 2 squared equals r squared. So 4 plus 4, that would be 8 equals r squared. Square root that. Hey, look at that. We're going to be able to find the radius. So what do I get? I get that the radius is root 8, which I'm going to simplify down. Or, you know what we could do? We could go back and remember that when I need what I really need, even more than I need the radius, I really need to know what r squared is because the equation of a circle calls for r squared. Now that I know that, I can quickly and easily write out the equation of the circle. X squared plus y squared equals r squared, and we know that r squared is 8. So that one's done. All right, y'all, that's all for today. Hope you enjoyed the video, and we'll see you next time.